Okay.
So probably I can take time to introduce Dr. Jiaqi too.
Okay.
So basically he's right now visiting me. Okay, so actually we were classmates when we were like college students. Okay. So essentially Jiaqi right now is associate researcher in Chinese Academy of Science. Right?
Yes.
And he has done his undergrad and PhD in Peking University. And later he went to University of the United States.
United Nation University.
Okay.
United Nation University in Macau. Yes.
As a postdoc
Yes.
researcher. And right now his research interests mainly on like mining, including like wave mining and anomaly detection. Actually his background is a little bit in formal methods.
Yes, yes.
Logic, so he actually switched
Yes.
significantly after PhD degree. Okay?
Yeah.
Which happens sometimes, but not that much. Okay? And one additional thing I want to mention that actually Jiaqi is a top bridge player. He has won several like national champions, I guess.
Yes, university championship.
Okay, I think they also kind of
National university.
national university.
Yeah, yes.
Anyway, he's very good at playing bridge. So if some of you are interested, like learning playing bridge or like to do some bridge training, so you actually you can find him. Okay, so now probably it's time for us to attend this talk right now.
Okay. Okay, thank you, Yizhou, very much. Okay, good morning, everyone. I'm Jiaqi Zhu, a visiting scholar of Yizhou. I come from Institute of Software, Chinese Academy of Sciences. My research focuses on the web mining, anomaly detection, and complex event processing. As Yizhou mentioned, in PhD, my research focused on formal verification, the temporal logic. So now I want to do some cross work to cross the discipline to make some new research results. This today's talk is a point to connect my previous work on the data mining. This is unsupervised rare pattern mining. This topic is a little different from the previous topic of this seminar because in our application scenario of anomaly detection and rule detection, most of the things we want to discover is totally unknown to us. So we don't have enough labeled data to do the supervised learning. So this is why we have to do unsupervised mining, and the rare pattern mining has a close relationship to frequent pattern mining. This is a fundamental part of data mining, but this is different because okay.
So you say rare pattern mining.
Yes.
And then for me, rare pattern mining is negation of the frequent pattern mining. So
Yes.
pattern mining, then you can do rare pattern mining.
Yes, I will explain that later and to see how we should define the rare pattern mining problem. Yes. Yes, for the,
Too many real patterns.
yes. So we want to find the rare but significant pattern, but not all rare pattern. We want to find the rare but significant. So we need to define what is a significant rare pattern. Yes, that is the objective of this problem.
I know nothing about this. I think that's why I have no these things. But in terms of saying what is saying that there are too many rare patterns.
Yes.
That one, I don't necessarily agree. Why do I don't agree? Because once we find all frequent patterns, then if we define everything else is rare, then just remembering frequent patterns just give us the power to identify all rare patterns, right? So simply by negating it. And the second thing is that when certain patterns are very rare, I'm not sure unless we somehow use side information, side channel, to define what is significant and what is not significant. just from the data itself, I don't think it is any way possible for us to tell whether something is rare but not significant, or something is rare and significant.
Yes, that depends on the application, the scenario. Yes.
So there is now, when you go into there, is the rare pattern mining is not really a task of mining, but more of our definition, what we actually define based on our inherent knowledge.
Yes,
based
yes.
on the data, based on our perception about the world.
Yes.
We define what is important and what is
Yeah.
not important. And
Yeah.
that has nothing to do with the mining, I think.
Oh, yes, yes. Indeed, the most important thing is to define what is a rare pattern, and you will see the algorithm is similar and just extended from frequent pattern mining, but the most contribution is the definition of the rare pattern. Yes, it's very true. Yes. And from the approach view, it's also different because the downward closure property of frequent pattern mining does not hold here for rare patterns. You will see it later. So it brings a new challenge to the definition of the rare patterns and the approaches to mining them. Yes. So there are two points of difference. One is a problem definition, and the other is the approach. Because the key problem is downward closure property does not hold here. Yes. This talk will divide it into three parts. Firstly, I will introduce the background of the problem we want to solve, that is anomaly detection on the internet. And then I will give a simple survey of unsupervised rare pattern mining. This is a journal paper, TKDD, in 2016. For the third part, I will present my own work on discovering personalized and abnormal user behavior on the internet. We define it as a kind of rare pattern named user-aware rare sequential topic pattern, and we have some successful real applications on the suspect discovery of economic crimes. I will demonstrate it later, but not very detailedly, just to talk the content can be public. Yes. First, we look at the background of this problem, that is anomaly detection on the internet. I will start from a familiar problem, that is fake news detection, and then go to the motivating problem. We all know that on the internet, on the social media, there are many news and messages, but some of them are fake. Even some of them are published intentionally to mislead other users to realize his goals. To realize his goals, and even we all know that it has a negative effect on the online information diffusion and offline society. It even affected the president election of U.S. So now fake news detection on social media has recently become an emerging research direction, especially on Facebook. Facebook itself and some other company have developed some AI tools to detect and identify the fake news automatically. For example, when we look at some messages in Facebook like this, it said the sky is no longer blue. We all know this is a fake news, and it will automatically have an alert said it is probably fake news. But how do this technique realize? And now there is a survey paper, Fake News Detection on Social Media, a Data Mining Perspective. This is published in CKDD Exploration 2017. This is others' work. They said currently the fake news detection problem is mostly defined as a binary classification problem. Most of the methods are supervised method. So it takes two steps. The first is feature extraction, and the second is model construction. For the feature extraction, we can extract the features of news content like linguistic-based features, the visual-based features, and the social context features. For example, the user-based features, the post-based features, and the network-based features. And in the model construction part, they will construct a model for anomaly or for normality. The models are divided into two parts. One is supervised classical models with a large amount of label data, and the other is semi-supervised models leveraging social engagements and relationships. But there are some limitations of the methods for the fake news detection. Firstly, it needs a large amount of label data with ground truth. Second is it regards messages individually and separately. So it determines whether news is fake or not. Just from the message itself, and maybe the information of one message is vague and cannot represent the complete behavior and the latent intention. So that is our thought. Our thought is to find the complete behavior of a suspect, but not just a point behavior of one message. So in the existing methods, there are from one message to the account, because we want to determine whether an account, a user on the internet is suspicious, but not just a message. The existing work is based on the aggregation of the fake score of individual messages and the similarity of the fake scores published by the same person, or all the users have a strong relationship, but does not consider the correlation of the contents. So we will consider the correlation of the contents to capture the complete behavior. And this is the project we are working on. This project is to do the anomaly detection on the internet. It is collaborated with Economic Crime Investigation Department, Ministry of Public Security in China. They want to find some clues for latent criminals from the internet, from the social media. And the whole project can be described by this figure. This is a three-layer network. In the first layer is the internet, is the social media, and people publish some messages on the internet. And we will find the correspondence of these online users to the real identity. So there are some real identity relationship on the real society. And at last, we will connect this entity to their capital transaction. To the capital transaction to find some anomaly. So this is the whole picture. But in this talk, I will focus on the first step to find some clues from the first level, from the first layer, the internet layer, to find some latent criminals. That is the motivating problem. Yes. Okay. Yes. Okay. Okay. So we can. Okay. First from this and the next slide. So So we can abstract this application scenario to the research problem. That is to discover personalized and abnormal user behaviors from messages published on the internet. Specifically, we want to find the internet users with special tasks or goals, so they are latent criminals, and analyze and infer the real and latent intentions behind their messages on the internet. We can see an example. There are many fraud in the microblog. For example, the lottery fraud. When some internet user want to commit a lottery fraud, he will first send a message about a word temptation, and then he will diddle the information of other internet users, and then he will obtain some fees from other users, and at last, if his object does not realize that he will take some intimidation. So his behavior is reflected on a sequence of messages he published according this order. So this is an example, but for some emerging crime, for some emerging behavior, we don't know the content of each step. So what we want to do is to first build the correlation among successive messages published by a specific user, and mine rare but significant patterns, and meanwhile find associated users in an unsupervised way. So this example is example we know the behavior, so we can detect each step. But for most of the crime, they are new, so we don't know the content of each step. So our task is to mine the sequential patterns of their behaviors from the large amount of data without any supervised data. Yes, that is the problem we want to tackle. Let's go back the problem. The problem has no ground truth and label data for classification, as mentioned in fake news detection. So it is more complicated than fake news detection. Because binary classification is not suitable here. And also there are no regularity for normal behavior for clustering. So clustering is also not suitable here. So we must do this thing by a mining problem, a mining approach. That is, we want to mine the rare but significant patterns. Here, the significant patterns is means it indicates the user have a specific target or goals and the intentions. Yes. Now I will first give a simple survey to unsupervised rare pattern mining approaches. The first is the basics of frequent pattern mining, and then we look into the problem of rare pattern mining compared to frequent pattern mining, and introduce some mining approaches. These are the things in the slides of Yizhou's class or some data mining class. That is the frequent patterns. I think both of you are familiar with it. So I just give a very simple survey. Simple review. By an example, for this example, we have 5 transactions and we have 6 items, and we want to define whether an item set is frequent. That is, we first define item set as a set of items, and the absolute support and the relative support. We usually use support as a relative support. That is a probability that a transaction contains X. For example, the AB item set, its relative support is 0.6 because it's 3 over 5. There are 3 transactions have contain AB, but and there are totally 5 transactions. So the relative support of AB is 0.6. We define an item set X is frequent if and only if its support is no less than a threshold. For example, if we set the threshold min sub is 0.5, we can see that the AB item set is a frequent pattern. Okay. Okay. Oh, sorry. Yeah. Yes. Sorry. Yes. Sorry. There should be 2. Yes. And the sequential pattern is a special kind of patterns. The difference is that the order matters in the data set. So if we change the first transaction ABC to BAC, it is a different transaction, and it will affect the absolute support, the relative support, and whether it is frequent. So if it changes to BAC, the sequence AB is no longer frequent because its support becomes 0.4. It's less than 0.5. And there is another kind of patterns, that is association rules. It has an antecedent X and a consequent Y. For example, if A then B, and besides the support, we define the confidence of the rules, and it is a conditional probability. For this rule, it can be computed as 0.75. And for the association rule, we define whether it is interesting or strong. It has 2 criteria. The one is it has a high support. The other is has a high confidence. So the frequent pattern, the criteria of the frequent pattern is high support plus high confidence. That is different from rare pattern. We will talk later. And for the frequent pattern mining, important property is downward closure property. That is, if an item set or sequence is frequent, its subset are all frequent. Based on this property, there are some approaches with pruning strategy. It can be divided into two classes, a priori based and FP growth based. We will not talk it in detail. Now we enter the rare pattern. Now we see how we want to find the suspect on the internet, like as I mentioned in the problem, in the motivation problem. So we want to find is abnormal or suspicious behaviors. They are less frequent. So we want to define the rare patterns instead of frequent patterns. There is a simple definition. That is, the rare patterns are opposite to frequent patterns, like the Joe said. Yes, but if in this simple definition, we can define the item set X or sequence alpha is called rare, if and only if its support is less than or equal to the min sub. It's just the opposite of the frequent pattern. But this definition has problems because if the pattern is too rare, for example, if the pattern in the its support is very low, it also intuitively it is also not significant, because for the criminal's behavior it must be it must occur repeatedly, but not only once. Only once is not a crime. So if it is a crime, it will occur repeatedly. So very rare patterns is not significant. It may occur by accident. So we want to mine rare but significant patterns with low support but not very low. So in some existing work, they also add a min sub, a new min sub, a new threshold for the minimal support threshold, and transform the min sub of frequent patterns to max sub. So they want to find the patterns between the min sub and the max sub. This is most of the existing work of unsupervised pattern mining. But here we need to define the significant point. The significant point is no longer support, but so we need to find another point to indicate it is significant. There are two views to define the new significant point. The first one is high confidence for association rules. So in this part, the rare patterns is defined as low support but high confidence. This is different from the frequent pattern. That is high support and high confidence. And this is suitable for association rules, but not behavior patterns. So in our own work, we define another significant point of rare patterns. That is high local support. So even if the global support is low, but the local support is relatively high. So this is our significant point for the behavior pattern problems. The rare pattern mining can be the rare pattern mining approaches can be applied in many applications, not just the case investigation. We said in the case investigation, we can detect suspicious internet users from their publishing behavior and web usage. That is, I just said, it's globally rare but locally relatively frequent. That is characteristics of the criminal behavior, the suspicious behavior on the internet. And the second application domain is network security. That is to detect network attacks from wireless connection record. There are some existing work that in this domain, it defines the suspicious core of records. If a record has more rare patterns than frequent patterns, we think the record is suspicious. That is many existing work done. And the third domain is medicine. So we can detect adverse reactions or drug interactions from the case report. That is, maybe some frequent items could cause the rare item. Because the consequent is a rare item, so that is totally so the association rule totally is not a frequent pattern. So frequent pattern mining method cannot directly used here. So this is so this belongs to the rare pattern. So we need to design a rare pattern approach to solving this problem. For example, the elevated heart rate, fever, and skin bruises may be rare or frequent, but their combination will probably lead to low blood pressure. This is a rare item. So we want to find this kind of symptoms to get some rare rules of the relationship between the symptom and diseases. This is now there are also some works on this domain. This is the applications of rare pattern mining, the main applications. But as long as the domain has anomaly, the rare pattern mining may apply. This is a roadmap for types of rare patterns. This figure is borrowed from the survey paper in TKDD. The rare pattern can be it regards this problem in two aspects. One is a kind of rare pattern. The other is the data type. For the rare pattern, besides the basic types, that is rare association rules and rare patterns, it has some extended patterns. For example, the subgraph patterns, the probabilistic patterns, and sequential patterns. In this survey paper, most of the work they cite belongs to the part circled by blue. That is the basic rare association rule and rare pattern. But our work, I will talk in the next part, is it contains, it involves the probabilistic patterns and the sequential patterns. So this is an extension of existing rare pattern mining. And the data type has the sequential time series, the temporal structure graph network data, spatial co-location data, and uncertain data. Our work focuses on the temporal data and the uncertain data. So this is the survey of the roadmap for types of rare patterns, and our work's position in this roadmap. Now we look at the challenge of the rare pattern mining. Just we look at the problem of the rare pattern mining. From the problem point of view, the rare pattern mining likes to find a needle in a haystack. In Chinese, it's find a needle in the sea. Yes, so it lacks of data associated with rare cases, and the generalization of identifying regularity for this data is a difficult task. This is from the problem view. To be more important from the approach view, the downward closure property no longer holds, because we need to consider both high support items and low support items. In frequent pattern mining, we can filter the items to with the min sub threshold. So we can just look at the high support item and combine it to form an item set or sequence. But in rare pattern mining, we need to consider not only high support items, but also low support items. So classical pruning strategy is hard to use for a priori based method and FP growth based methods. And we need to set an appropriate min sub for the mining. If the min sub is too high, some significant rare patterns will be missed. This is not what we want to get. But if the min sub is too low, it will cause the combinatorial explosion in the number of generated item set. So in the rare pattern mining problem, this is a contradiction. This is a paradox of the approaches. But in frequent pattern mining, because we only consider high support items, so this problem is not obvious. So the current mining approaches, most of the current approaches is to to tackle this problem. The key point is to give a reasonable definition of rare patterns, which can be computed efficiently. Yes, there are 4 categories of approaches to define the rare patterns. The first one is with we use a variable support threshold. So different items and different items sets have different support threshold. That in this way, we want to overcome the limitations of the extreme cases, the min sub too high or too low. So if different item and item set have different support threshold, that is maybe alleviate this problem. And there are some other categories of approaches. For example, we can don't use the support threshold, but use other constraints, such as the similarity among the transactions among the data, or just confidence-based pruning. And there are also the consequent constraint-based approach. That is, we can predetermine the consequent terms with prior knowledge. So that will reduce the search space of the rare patterns. Okay.
But in the previous slide, you say that when the min support is too low,
Yes.
there could be too many rare patterns.
Yes, because that is a combination of items.
Somehow intuition is the opposite, right? So intuition says that if you move the min support to the low end, and the pattern satisfied that smaller than the support is smaller.
Oh, no. Oh, in this slide, using the min sub is this. But in this slide, I said that definition is not good. So we go to this definition. This definition, we define a new min sub that is lower than the original min sub, and we transform the min sub to max sub. So the min sub is this point, but not this point. So the patterns we want to find is in this range.
I see.
Yes. Okay.
In other words, it shouldn't be too low support.
Yes, we don't want too low support, but lower than the frequent pattern. Yes. Yes, because if a pattern has too low support, it's most of them occur by accident. So it is not significant. So in most of the existing rare pattern mining works, they generally define a new min sub, and some of them combine the min sub and the max sub. The max sub is the original min sub. Yeah. And the fourth category of the approach is the tree-based approach. It's extended the FP trees. It will make because the FP tree is an efficient way to mine the frequent patterns. So it borrows that idea and constructs some efficient approaches. In this talk, I will introduce in detail the first part with the variable support threshold, because other is complicated or trivial, like the third categories. If we have want to define a variable support threshold, that is, we want to overcome the limitations of extreme cases. The threshold for different items and the item size should be different. So there are many methods to define the variable support threshold. intuitively, because the formula is just the support of item set X in the data set D is no less than min sub. So we can modify either part of the equation, either the support value part or the threshold part. This is equivalent because you increase the red part is equivalent to decreasing the red part. So there are some work modifying the left part and some work modifying the red part. The modification is based on different factors. They can based on the frequency of items. They can be based on the general constraints on longer item sets and the significance of the items from other prior knowledge and the length of the item set. I will give some examples of this method later. And there are also some other methods. That is to specify the max-up for items or item set, and or define some boundary item set to reduce the search space. That I will also give an example. Now I will look at look at this part in detail. First is I will introduce some representative works. The first is multiple minimal support threshold. That is, we define for each item its own minimal item support. It is related to the frequency of that item in the data set. They first define least support LS, and it make a maximal value of coefficient beta times the support of the item and the least support. So in this way, we define the rarity of each item. After we define this, we can define the item set, the threshold of the item set as the minimal value of its each item inside the item set. So for the item set containing a rare item, it will have a low threshold. But if an item set have but if the items in the item set all have all frequent, the threshold of the item set will be high. So this is the idea. In this way, we can define different threshold for different item set and to overcome the limitation of extreme cases. So we differentiate we differently regard the item sets based on its items. But in this way, in order to make the process of candidate generation effective, the items need to be sorted in advance in the ascending order of their MIS values, because it must assure that when we check an item is possibly contained in the item set, in the later process, it will not be checked again for the small for the item set for the items with smaller MIS values.
What is
LS is a hyper parameter, is a least support. It let the MIS not it makes the MIS not too low. Because it is least support. So the MIS, so the value of MISI is no less than the LS.
Intuition behind this?
Behind the whole method or the LS?
I think both. I mean, also definition, like why we need this MIS for
Oh, because the yes, the key idea is we regard differently for different item sets, and if an item set has a very rare item, we want to mine it. If we want to mine an item set with rare items, we must set the threshold as a lower value.
I think what he's trying to do is that if certain event is very important, then even if it's very rare, we may actually want to detect it. So the example
Oh.
let's say the user account password information has been stolen, right? So that event happened. So what he wants to do is that event compared to other kinds of rare events, let's say the user's image files were stolen, right? So those are rare events, but we don't really care that as much as, let's say, the user's password information has been stolen. So he wants to set the mean support level at different levels depending on the significance of that event. So in case of, let's say, image files were stolen, maybe we want to detect it only if it happens many times. But when the password files have been stolen, we may want to detect it even if it happened only once. So we may want to set the minimum support threshold value differently, depending on the significance of that item or significance of that event.
Yeah.
So-
And it's automatically done.
So then,
Yeah, for example, okay.
so the beta factor,
Did-
the beta factor there, the maximum of the beta factor, that is what he tries to set. For every item, somehow he assigns the significance of that item.
Better.
Beta, yeah, the beta in the MIS of max
um,
beta.
Yes, beta is also a hyperparameter.
Well, hyperparameter that he sets for every item.
It's the
Yes.
same for
Same, yes, yes. Beta is same for is a fixed value.
Fixed
The-
value
the-
per item.
For what?
Per item.
Oh, for all the items.
Yes, for all the item.
For all the items. Then what
Yes.
is the per I, comma D?
Yes, but this guy is different for all items. This is the support.
Where did you define it?
Which one? This?
Yeah, the support of
Oh,
I,
this is the classical definition of support. The relative support of the item I in the data set.
Data.
Yes, it depends on data. So it first compute the support of each item, and then use this formula to define the threshold of each item set. So there's two steps.
what is LS?
LS is another hyperparameter, which is least support. So it makes the MIS of I not too low. So it is a least value of this value.
I don't understand that. Why, if beta is not item dependent?
Beta is not item dependent,
Beta is not item dependent.
but this is item dependent. The support value is item dependent.
So can you use the example like the password stolen to
Right.
Okay, so
Example to understand the intuition behind this. Otherwise,
okay, I can like for this rule, if this item is very rare, for example, support is 0.1, and these three item has a support 0.6. If this happens, if we set the beta equals to 1, so the MIS of these three items are all 0.6, but the MIS of this item is 0.1. And for the whole rule, its threshold will be set of the minimum of 0.6 and 0.1. That is 0.1. So that is to consider to protect the rarest atom in the atom set. Because in the frequent pattern mining approaches, if we set the threshold as 0.6 or 0.4, this atom will not be considered because its support is lower than 0.4. So this work, so the idea of this work is first get the support value of each atom, and when we mine the atom set, it need to protect the rarest atom in this atom set.
So this one essentially says that whatever is the rarest.
Sorry?
You just pick the value which is the smallest. That is
Yes. The smallest and the.
But there is no item customization then, because beta is a global parameter, global hyperparameter.
Yes, beta is global.
Essentially, what you are saying is that whatever item that happens to the list, we just use that as the support value of that particular.
If the for example, we can set the list support as 0.2. So if we set the LS is 0.2, the MS of this atom will become 0.2. But the MS of these three atoms will also be 0.6. So that is just to prevent MIS value from very low. So the MIS is just a middle quantity to compute the threshold of atom sets. Because we need to first compute this and then compute the threshold of the atom set.
You don't want to manually specify support.
Yes. Yes. For different atom sets, they define different threshold based on the atoms inside the atom set.
Why it couldn't be just LS?
Why it?
Because
Yes, LS. That is. I think that is to make our search not fall into this area.
No, I think the question
Yes.
is why in MIS, why can't it be just LS? I also don't understand why we need MIS.
So if we don't use MIS, you mean how to compute the different threshold for different
Just set MIS equal to LS.
to what?
To equal to LS.
If MIS equals to LS, it is same for all the items.
Advantage of differentiating.
It's like the that is from here. If the mean sub is too high, it has a problem, and is too low, it also has a problem. So we want to not consider the extreme case. So both this and this are extreme case. So all the atom sets have the same threshold. That will lead to problems. But now the idea is to let the different atom set have different threshold. If an atom set contains a very rare atom, the threshold for finding this atom set should be lower.
So what in
oh, this is not my own work. So I did. This is not my own work. This is just a survey. Yes.
That in the paper that you cite, what are the typical beta values that people use?
Oh, sorry, I didn't look at the experiment of this.
Ask it differently. Is the beta value typically higher than 1 or lower than 1?
What?
Beta value is higher than 1 or lower than 1? Larger than 1, like 2, 3, 4, or 0.5, 0.1?
Which quantity?
Beta.
Beta.
Yeah.
Oh, beta is less than 1. I think.
It should be larger than 1.
Oh, it's. No, because the support of an item set is lower than the support of the item inside it, right?
What is
The
I is an individual item.
yes, individual item, yes.
D is our data set.
D is that data set, yes.
From which we want to obtain whatever statistics.
Yes.
I think beta should be larger than 1.
No, because
Maybe a factor of 5.
because this quantity is used to measure the support of item set. Yes, the support of item set is lower than the support of items
Oh,
inside it.
I see. So much lower.
Yes, is less than 1. The beta is less than 1.
So I is an item or
Yes.
item type?
Item. This is for each item. I is an item. Oh, I should write I here. Yeah.
So I think I got the intuition. So here, I think what is happening is that, let's say there are two different kinds of items, right? One item that is very rare and one item that is not as rare.
Yeah.
In that case, if you use the same number of support to detect certain rare item sets, that includes, let's say, item A and item B, then it's kind of unfair because item B we will detect a lot more because of the sheer quantity of the item B happening so many times. So I think what this tries to do is that we want to set the support threshold differently depending on how frequent individual items are.
Yes.
If a particular item is very rare, then we want to set the support threshold lower. And if the particular item is less or much more frequent, then we want to set the support threshold higher.
Yes.
So
But
here,
why not just say, I want this number of real patterns?
Or just number.
So here you try to use this mean support to kind of control how many real patterns we want, right?
so the reason why he needs this is because he can identify the rare patterns only after he discovers it. So during the mining process, he needs some threshold value. And then he kind of wants to set the threshold value kind of proportional to the lowest frequency of the item within that particular item set. So this kind of recursive formula, the first set the threshold value as a factor of the support individual item, and then finding the minimum value among them. Somehow make sure that we set the threshold value as proportional to the minimum frequency of that item.
That makes sense now, because although like eventually they wanted to see for some item, I wanted to like similar number of real patterns, but that actually cannot be achieved because anyway they have to specify mean support. Okay.
Yes, in a pattern we want to find there may be some rare items and maybe some frequent items. So we want to we want to protect the rare items. Yes, this is the idea. Yes, similar work to this is to modify. This is to modify the red part, to modify the threshold part. And a similar work is to modify the support part. So the support can be a relative. I read this wrong. This is modify the support part. The support of item set I1 to ik is defined as divided by the minimum value of each item in the item size.
It's kind of normalized version.
Yes, that's like a normalization. Yes. Yes, this is similar ideas.
Is there any other threshold related? Because suppose like I want just appear once, right?
Yes, if I want just once, yes, the support is
It's gonna be huge.
yes.
One divided by, I think it's relative support, right?
Yes.
Yeah, if it's relative one, then if I want just appear once, then the main value, denominator is going to be a very tiny number,
Yeah.
and then the house is going to be a huge number. So I
Yes.
think that definition is not robust.
Yes. So, but
Probably, yeah, I think a better way is like also have something else.
yes. Maybe yes.
For this one, does it still guarantee the priority property or we call it downstream property?
Oh no. All of these methods don't have that property. Because the
Find all the patterns from smaller one to larger one.
that is the because we cannot use that property, so the algorithm has less pruning, but just less pruning. The whole process is also okay, but just pruning is not okay. So the search space is a problem, but the framework of the algorithm is also there.
But if we cannot efficiently do the pruning,
Yeah.
not just use find all the patterns, right? We have two support thresholds. Even though the mean support is very low, then when we find many patterns, but still
Oh.
right.
Oh yes, but it because it is in this range. Actually, this range is smaller than this range. So for the whole search space, it's actually small, not too large. Because we restricted with two thresholds.
It depends.
Yes, it depends. It's just intuitive idea, yes. And later there are also some works to demonstrate how to do the search.
Those that work, but if we think about the simplest kind of optimization that you can do, depending on these different levels of minimum support, is that because that definition is dependent on the particular item,
Yeah.
very rare item existing in that particular world. Only then we lower the threshold value. Right? So a particular frequent item set, that their threshold value is whatever the minimum value of whatever items that appear there. Right? So during our mining stage, what it can do is that in principle, we pick the lowest threshold value and then identify everything with that lowest threshold value. That's what you're proposing, right? But the improvement or optimization that you can do is that we start with that, right? But what you have to keep in mind is that whatever frequent pattern that you have to mine, let's say the lowest one, in the beginning we have to use that lowest threshold value. But once you do the two-pair item, other items that doesn't appear with that lowest frequency one, we don't have to keep that lowest frequency anymore. Right? Because those are not appearing with that one. So the threshold value is higher than that one. I don't know whether it
I
makes
think
sense.
maybe in the very beginning step, this help, right? For single.
Well, over time, we can actually gradually increase the minimum support values for the item that doesn't appear with that least frequent one. I think that is the kind of optimization that is easily do. Because let's say item A, B, and C, right? Item A, B, and C. If A has very low support value,
Okay.
right? assume that A, let's say A,
threshold.
A, if A never appeared with B, and A never appeared with C, then we know that B and C, we don't have to lower the threshold value anymore. B and C, any items B and C, because it will not appear with A anymore, right? So the support threshold value that you have to keep track of B and C is actually higher than the support threshold value that is kept for A. Yeah. Because now, because there is no frequent or rare item sets that we have to mine from the data set, right? So what we can figure out is that once you identify the pairwise support threshold value, whatever that doesn't appear with A, now we can increase their support threshold value. So that is kind of a very simple optimization. As we kind of gradually go up, whatever doesn't appear with A, we can kind of gradually increase their support threshold value. So it will be much more prudent than just using the lowest value. And I'm sure there are a lot of people, I assume, so I'm sure they're figuring out exactly when you can increase the value. There are a lot of optimizations.
Yes, if we first sort these items in the ascending order of their MIS value, it is more efficient because we can just, if a value we give up earlier, we cannot search it later. So this is an effective point of this method. Okay, and there is also a approach of adaptive a priori. That is the opposite to the last two works. The last two works is define the threshold from atom to atom set, from short atom set to long atom set. But this work is define the support constraints from long atom set to short atom set. That is depend on the prior knowledge. Maybe we know that the combination of A B is significant. So maybe we can set this set the constraints on this atom set lower. If the atom set is not so significant, we can set it higher. Yes, that is the intuitive idea. And each constraint applies to all of its superset. For example, if the support constraints of AB is set to 0.2 and B set to 0.4, C set to 0.5, how do we compute the threshold of ABC? Because the ABC contains AB, B, and C, so we take the minimal value of all the constraints as its subset. So this value is 0.2. But for B and C, it only contains B and C, but not contain AB. So this threshold is 0.4. This is from some prior knowledge of a longer data set to define the constraints from the longer level, from the longer atom set level. Yes, this is another work. This is another method we can use to handle this problem. And this is a more generalized method. That is to define a weight. The weight, we first define the item weight. It represents its significance with prior knowledge, and then define the weight of a rule or an item set as the average value of the item weights for all the items inside the item sets. And then we can define the weighted support as the original support times the weight of the item. This is the modification from the left part of the yin equation to make the support weighted.
So how to set those
Weight.
This is
Yes, yes. Yes, that is from another from other points the significance. So this is different from this work because this work the MIS it depends on the data. Yes, but in this work it is not dependent on the data. It depends on other prior knowledge. For example, if we want to, if we pay more attention to fever, so we can set fever a higher weight. Yes, this is from other prior knowledge, but not the data itself. Okay. For this work, if the weight satisfies some property, even though the downward closure property does not hold, but there may be the weighted downward closure property. But this needs to be deduced for specific problem. But there may, but the property may exist, and some algorithm first deduce this property and then apply it to the mining algorithms. And the other, another work is LP miner and SLP miner for sequential pattern mining. This is for item set mining. This is for the sequential pattern mining. The idea is the support threshold. We let the support threshold decreases as a function of the item set length. So this is depend on the weight. You can think there is a weight, but it's not just the multiplication. It as a function of the item set length. So there is so you can think there is a line of the threshold. This threshold for the low length, for item set with low length, it has a high threshold, and for if the item set is long, it has a lower threshold. But in this work, the downward closure property does not hold. But there is another property that is the smallest valid extension. That is to say, if an item set S is in this position, it is below the line, so it is not significant. But we can know how long we extend it. It is possible to become significant. So this has this property. So using this property, the mining algorithm can be more effective, more efficient. This is this work. Oh, and this is the last work I introduced. This is the how to realize the search process. This work gives a method. That is to define 3 types of item sets. The first one is minimal generator, denoted as MG. They have a lower support than their subset. So it can be regarded as a generator to generate some minimal rare item set, denoted as MRI. MRI has non-zero support, and all of its subsets are frequent. So it's a minimal rare because all of its subsets are frequent. So from the MG, we can generate MRI, and all the patterns smaller or contained by the item set in MRI are frequent item set. And in the other direction, we also define minimal zero generators. It has zero support, and all of its subsets have non-zero support. So if For all the item set containing the item set in MZG, it is an insignificant item set. So we first find these two set of item set and to do the search just in the middle of here to extend the item set in MRI to the item set in MZG. So this is the general framework of the searching process. It is proposed in this work. Okay. Okay, we make a simple review of the method we just mentioned. The existing unsupervised rare pattern mining approaches are focused on association rules, and the significant point is high confidence. Just the searching process, the criteria of the searching is low support but high confidence. Because high confidence part is similar to frequent pattern mining, so the existing work mainly to solve the low support problem. So we just pay attention to the low support problem, but the criteria also contain the high confidence. But for our problem, for the suspect discovery problem, the significant point of the rare behavior patterns is high user-specific support. This is different from existing works. And most of the data sets of existing work is deterministic. Even though there are probabilistic data set for the frequent pattern mining, but there is no work of probabilistic data set for rare pattern mining. For the deterministic data, the support value is a deterministic frequency or count, so it is relatively simple to compute. But for our suspect discovery problem, the dataset on social media are short and irregular texts. So the content of each message is hard to obtain deterministically. So the data as the input of our problem must be probabilistic. So this is we want to solve the input data is probabilistic. So we must define the expected support, and the rarity needs to be measured globally based on the expected support, but not just support. Okay, now we enter our work. I can talk it a little simpler. The contribution of this work is mainly 3 points. The first is we put forward a concept of sequential topic patterns to build the correlation among successive documents, successive messages published by a specific user to find the that is the second part. The second point is we formulate the mining problem of user-aware rare STPs in order to characterize and discover personalized and abnormal behaviors of internet users. And the third point is we present a framework to pragmatically solve the problem and design a group of effective and efficient algorithms to support it. This is published in the preliminary idea is published in SDM 2014, and the later work published in TKDE 2016. And this work has also successful real applications in the suspect discovery for the economic crimes. We look at the problem formulation quickly. We first define the topic level documents. Because I just mentioned the messages on the internet is short and irregular. So key keyword-based method does not work very well. So we use the topic level document. So we first use topic models to extract topics of each messages of each document. This is can be regarded as a pre-processing of our work. So each document is expressed as a set of pairs. Each pair contains a topic Z and a probability P. But notice that here we can do a selection. So not all the combination of all the proportion of all the topic proportion is expressed here because we can set a threshold. Only the probability exceeds the threshold. We put it in the topic level expression. Yeah. Yes, but the topics we set is not very high. It's 10 and 15. We will see it later. So it's not very small, but we can also filter some very small probability. Yes. And the topic level document forms the document level document streams. In each document, we associate with the user, the author of the messages, and the time of the publishing. Yes, and we assume that at any time for any specific user, at most one document is involved. And this is a key concept of our work. That is, it defines the sequential topic pattern. This is defined as a sequence of topics. We want to make want to build the correlation of the successive documents of a specific user. For example, this is one user. He published many messages, and we think they are correlated. So we define the sequence of topics, for example, Z1, Z2, and Z3. And the instances of the patterns comes from the topic level document stream. We can do a matching. So if in this document there it has Z1 with probability 0.4, this document has Z2 with probability 0.6, and this document has Z3 with probability 0.5. So this is an instance of the pattern, and its probability is a multiplication of the three probability. This topic level abstract and semantic information is beneficial in finding regularity of users. But a keyword-based method cannot do this. So we use the topic level document. And here, each pattern represents a multiple step complete behavior of that specific user, which occurs repeatedly for specific users. So this is consistent with our motivation. We want to find some complete multiple step behavior. And that behavior occurs repeatedly. So that is our motivation, and this the definition consists of that motivation. And we define the support of the STPs. It is based on a session set. As the session, each session, we can think each session as a transaction in the classical pattern, frequent pattern mining. So we will first get the session set and define the support of STP alpha in a session set. It is an expected support. It defined as the average of the probability of the pattern occurs in each session. this definition has been similar definition has been used in other work, but for frequent pattern mining of probabilistic data. Here is our point. Is we think that we want to compare among all the patterns with different lengths, but from this formula we can see that the support of pattern is a multiplication of probability. The number of the probability is the length of the pattern. For example, the probability of this instance is the multiplication of 3 probabilities. So the patterns with different lengths have different order of magnitude of the support value. So we want to normalize it to compare it fairly. So here we make a simple method. That is, we compute the scale. We define a scaled support that is defined as the original support to the power of 1 over n. So by this step, we make the support value to a same order of magnitude. That is just a single probability. So we can compare we can compare the patterns with different lengths relatively fair.
Log scale better? It doesn't feel it just 1 over n, kind of too sensitive.
Cannot
Too sensitive to the less than. If you take a log.
log. Okay, you mean log and
Yeah.
okay.
It's just based on the reading of many other papers when they come to this issue. Okay, so like synthesis burns, there are different lenses. So if they want to take that into consideration, they usually want to use like log n as a factor.
But in those works, they also involve the multiplication of probability.
It's different.
Yes, because here the idea is just from the computation of this value. This is the multiplication of yes. So
We want to make the probability comparable. It's kind of average probability for each item.
that is the probability of a pattern's instance. So it must be a multiplication.
Yeah.
Yes.
I try to understand why this is reasonable. Sometimes the sequence has 3 items, then it's going with length 3.
Yes. So it's a multiplication of 3 probability. So we want to normalize it to 1 probability.
Yeah, it's kind of geometric mean, right?
Mean,
Geometric mean.
but mean.
Not mean, geometric means. I
Not
think it's kind of similar to that. It's like multiply them together and then take to the power of 1 of n. So it's kind of geometric mean.
Okay.
So
Okay. That is same. The geometry. Yes, it's same. Yes.
yeah, it's a comment.
Oh, yes. I should express it in geometric mean, but not the here. Yes. Okay. Yes, and this is for a given S. Now we define it associated with our input, our topic level document stream TDS. That is the scaled support of STP alpha in TDS. This is defined as we just get the session set S from TDS. And this is another pre-processing step in our approach. I will talk it later. If the session set is given for a specific problem, we can omit it in the definition, so just scale support of alpha. And we also define the scale support of alpha for a specific user, U, that is rated in this way, and this is in this session set is obtained also from the TDS, but only the document associated or published by the specific user U. So this set is a subset of this set if we restricted it by a specific user. And using this definition, we can define the user rarity of the patterns. And this is to do the regularization of the scaled support in two levels. The first level is in the user level. In the user level, we make the difference between the scaled support of alpha restricted on U and the scaled support of alpha globally. And the second step, we make the regularization in the pattern level. In the pattern level, we make the difference between the absolute rarity and the average value of the absolute rarity for all the patterns of U. That is, all the patterns that occurs in U. And in this way, we define the relative rarity. And the concept is user rare. That is globally rare, but relatively frequent. And given a topic level document stream TDS, a scaled support threshold HSS, and a relative rarity threshold HRR. So there are two thresholds for the two criteria. The first criterion indicate it's globally rare. So it's expressed as the scaled support of alpha globally is less than or equal to the first threshold HSS. And the second criteria is the relative rarity of alpha restricted on U is more than or equal to the second threshold HRR. And this is the definition of the rare patterns we define. And in the some reviewer said it's this concept has both the theoretical and practical significance. Some reviewers said it's put forward a new research direction in web mining because it defines a new kind of patterns for rare event mining. And it can be applied in many real-life scenarios of user behavior analysis. This is the framework of the approach. We first crawl some documents, some messages from internet, and then we do the data pre-processing. The data pre-processing has two steps. The first is topic extraction using some topic model. And the second step is the session identification to get the session set we just mentioned. After that, we will do the main things of the mining. The first is the STP, the pattern candidate discovery. That is executed for each user in parallel. So for each user, we execute a procedure of STP candidate discovery, and they will be executed in parallel. And then we will integrate the results to do a user-aware rarity analysis. This is a simple instruction for the topic extraction. We use Twitter LDA because the messages is very short. So Twitter LDA is more appropriate than classical LDA, and plus threshold-based filtering. But Twitter LDA think each message has only one topic. But here we use a probabilistic topic. But so here we get the probability through the training process. For the process of the GIPS sampling, we can get the probability of the topics, because it's maybe not a completely convergence. Yes. And for the session identification, we use the time interval heuristics. We think we divide each user session separately, and we think the time interval of any two adjacent messages in each session is less than or equal to a threshold HTI. So if two adjacent messages published by a specific user is larger than the threshold, we think it starts a new session. So that is the heuristic we used in our approach. And for the STP candidate discovery, we compute the scaled support of each STP for each user with pattern growth. That is belongs to the FP growth algorithm, but fit for the sequential patterns. And at last, we make the user-aware reality analysis according to the definition of the two measurements, the two criteria. Here, this is the details of this part, the STP candidate discovery. It is a recursive algorithm based on pattern growth. We think you're all familiar with the pattern growth, but here we extend the classical prefix span with probability calculation. This also have some existing work, but we changed it to make it more efficiently by defining a structure alpha prefix triples pref alpha, and it is a dynamic programming based algorithm, but actually the modification is not very big. So this is not the main contribution of the work. The main contribution is the problem. Yes, this is just a small modification of the existing algorithms. And we also design an approximation algorithm. In the approximation algorithm, we don't compute the probability of a pattern occurs in a session exactly, but we think it is equal to the probability of the instance with the maximal probability. And in this way, in the experiment, we find that in this way, the result is similar. Is not the difference of the result with the exact algorithm is not very large, but the efficiency is better. Now we look at the experiments. The experiment here we look at the real data set. In the paper, we use the Twitter data set, and the data set has two data sets. One is the general data set, the other is the sports specific data sets. And we set the parameters, some hyperparameters. For the pattern length, we use the 2, 3, and 4. And for other parameters, we just set it manually and to try some different values and to get a better one. But now we are also thinking of how whether we can learn the better hyperparameters automatically. This is one of my students are thinking, but it seems a little harder. For the evaluation of our work, we evaluated in two parts. The first part is to see if our approach can find some special users on the Twitter. And the second is to find whether our approach can find interpretable and reasonable patterns. We first look at the first part. We mainly pay attention to the top K users in terms of relatively rarity because they are more significant, so is more likely to be suspicious or has a personalized behavior. But in this problem, we don't have exact ground truth because in Twitter we don't know. And there is no strict definition of which users are abnormal or has personalized behavior. So we can just use approximate ground truth. That is, in Twitter, users can mark itself as verified. And we use this as approximate ground truth. We compared it with the baseline, it's the topic-based rarity analysis and the LDA for topic extraction. The results that our approach mined, the users mined by our approach are inclined to verify users. So our approach is capable of finding users with distinctive behavior patterns. Yes, but here we can understand the gap of our result and the approximate ground truth because the special behavior of ordinary users. So that is the special. So here we find the special behavior of verified users. But the special behavior of verified users, that is the gap between our result and the approximate ground truth. Those part of users are probably abnormal and should be investigated. So that can be understood in this way. And the second part of evaluation, we see whether we can find some interpretable and reasonable patterns. For example, we find two patterns, two users with special patterns. The first is the user 125. It have the patterns 8 and 14. Those are the index of topics. And the second is 13, 2, and 8. We check the top words of the involved topics from the output of the topic model and get a simple description of each topic. They are respectively products, buying, house, and playing. So we can make a conjecture. The user 125 is probably a sports fan because he has a pattern from first buying and then playing. And the other user is probably an internet cosmetic salesman because he has a pattern house to products to buying. We check this result in the real messages and the profiles of these users and find our conjecture is right. This is for the general data sets. And for the sports-specific data sets, our approach can distinguish different roles of users in the specific field and find the typical users for each role. We find 4 kinds of users in the sports field. That is players, journalists, ordinary fans, and commentators. They have different patterns. It is more interesting that for the journalists and the ordinary fans, their patterns have the same topic sets. broadcasts and NBA players, but the order of them is different. That can be interpreted intuitively, because the journalist maybe first give broadcast messages, and then to introduce the NBA the players involved in it. But for the ordinary fans, they first express his love on the players, and then to cite some broadcast news. So it indicates that if we just look at the topics or the content of each message, but not correlate them, we cannot distinguish the two kind of users. But in our approach, because we build the sequential correlation among the successive messages published by a specific user, so we can distinguish the different users on the internet. Here is a real application of our approach. This is not in the paper because the data set cannot be public. So I just give some interesting result. And the data set is a group chat record derived from the mobile of the criminal detained by the police. So here, our goal is to find other suspects besides our known criminals, the other suspects which are the friends or the group friends of the known criminals, and infer their behavior patterns. Here are some results of the patterns of recruitment for illegal organizations, and for example, the fundraising. We find some new type of some new means of committing a crime on the internet. And the first is the deception type. That is first to give some dream realization, and then go to the working detail. And the second is the inductive type. It's first to let the users to make some mobile operations, and then naturally, seemingly naturally, it transforms to recruiting details, and to make the users think it is very natural to go to the recruiting details. And the third one is also interesting. That is for the pyramid, the pyramid crime. For the pyramid crime, we find a pattern. That is first the criminal will talk some love affairs to other users, and then talk about working, and at last to go to the essential thing, the pyramid setting. And we also now we are currently doing the extension work. We are extending the individual patterns to community patterns. I just mentioned is individual patterns for a specific user. But for a criminal gang, for a criminal community, there may be also some patterns. For example, for the counterfeit case, there may be a patterns of the first the raw material acquisition, and then the production of the counterfeit, and then the transportation of the production, the product, and at last the illegal sale. So these steps should be reflected on the messages among the criminal community, and we want to mine this behavior pattern. And based on the pattern, we can better analyze the community. For example, the community with the specific task they want to commit, and the organizational structure of the community, and the roles and the important degree of each member of the community. But there is from the research of the view, there is a challenge. There are a large number of overlaps among instances of patterns, which makes the instance definition and the uncertainty computation complicated. So So we are thinking how to define it and how to compute it efficiently. And this is a preliminary try for this problem, and we use the private chat record, also derived from the mobile of criminals detained by the police, and we rebuild the hierarchy of the criminal gang and get the relational network, the hierarchy of the community. But this is different from classical method. In the classical method, the construction is based on the frequency of the communication, but not the content of their message. So that is not exact. But in our approach, the hierarchy is constructed based on the behavioral patterns mined by our algorithm. So they are more targeted to the crime. So this is more exact. Yes, and this is a preliminary try, and we are trying to modify and optimize this method. Oh, okay. That is for the future work. Our future work is to extend this work, because this work is just a preliminary work. It has some point can be extended. The first is the algorithm optimization. We can try to improve the parallelism and design the incremental and online algorithm. So not just do it from scratch to take advantage of some result of the previous mining. And the second part is we can extend the sequential patterns to complex patterns, because now the sequential patterns is just a simple case of complex event patterns. Because in my PhD, I worked on the temporal logic and some complex events expressed by temporal logic. So we want to, so we think whether if we add some timing constraints or some interleaving steps, it is more consistent with the real application. For example, we can restrict the successive for the successive steps, the time difference is less than or equal to a threshold t. And we can also think the maybe in the sequential patterns some topics the order is not sensitive, so we can define an interleaving step instead of all the sequential steps. And we can also think extend the publishing behavior to other behavior patterns. We can for the offline behavior, because in the figure I show in the beginning of this talk, there is a three layer network. So we want to correlate the online behavior to the offline behavior. We can regard each footprint or action of a user as a word published by him. So they can connect it with the publishing behavior and to mine some more hidden, more latent patterns of the users. Okay, and for the application part is also the crime investigation. We can now we focus on the economic crime. We can go to other types of crimes, and we can combine unsupervised mining with the experience and the knowledge of police, and we can do the interactive mining and the detection. So that means the mining can give some result, and the police can filter and select some result from the result derived automatically, and then so it is an iterative framework between the computer and the police. For other scenarios, it can also applied in financial internal audit, and this is we are currently working in a project collaborated with China Bank, and they can also apply to credit risk assessment. Okay, thank you for your attention. It's too long time. Okay.
Yeah, a lot of content.
Okay.
Thank you for coming. And we will have another presentation 2 weeks from here.
2 weeks?
Yeah. 2 weeks later. Not next Friday. Next Friday.
Okay.
Oh, 2 hours. It took-
It's perfect timing now.
这